Please, the floor is yours, Yassid, and thank you for coming.
Thank you very much. Okay, so, well, thank you very much to Félix for inviting me to come here. I think it's a very nice place to visit. You actually have quite a lot of money here. It's rather impressive, and you'll a little bit jealous, so it's nice. So I hope that we can start working together very soon. And what I'm going to present today, it's kind of like what we do at low-energy nuclear physics in the low-energy nuclear physics domain in terms of detectors that are mostly inherit from high-energy physics. So here I'm going to highlight not only a very specific technology, gaseous detector for detecting particles, but also I will explain some very fundamental physics problems that we can address with this and some experiments that you will find, at least, I hope, curious. So we do quite a lot of things in terms of nuclear reaction, but these experiments are kind of curious because are of general interest, let's say like that. And of course, there will be some link with the transfer of this technology that we are developing for these fundamental physics experiments into the, well, what Félix mentioned, its applications in the domain of neutron imaging and so on. I'm not going to explain that because otherwise we'll be here for quite a lot of time, but in any case, you can ask me at any point. So this is something that I usually rescue and salvage from other presentations for the CERN collaboration on gas detectors, the RD1, and this is something that I had to present during the school. But just last year, we had the anniversary of the invention of the time projection chamber, which is a very specific detector for particles physics. And actually here, there's quite a lot of developments on this. But in this program, in this talk, what I'm going to talk about is differences between high energy physics and low energy physics, just to highlight that we have also some problems there. And also, in general, what I'm going to explain is why or how do we use those detectors for addressing some specific problems. As you will see, there's quite a lot of things. I removed some of them. And in particular, I will talk about rare event search, applications, and neutrino physics as well. Okay, so not the physics itself, but the technology to address those physics. So now the question is, why do we study low energy nuclear physics? So the atomic nuclei that sits here in the middle of what we call quantum ladder, it's actually a perfect laboratory to understand quantum phenomena. So you know that this year is the year of quantum technology, and everybody is so hyped about doing a lot of things with quantum physics, simulators, computers, and so on. But in reality, what they do is what we have been doing in nuclear physics all the time, because it's trying to understand how many bodies connect, and they give the appearance of other emergent phenomena in nature that could be in more complex systems in this quantum ladder, from very tiny size, like could be superstring, to very big objects, like could be galaxy clusters, galaxies, stars, and planets. Because reaching these is usually complicated, understanding these phenomena, or how the what we call the many body problem, right? How we can put all these things together will help us to understand all this. Okay, so this is why we do this. And in reality, if you know something about quantum physics, the nucleus itself, it's an open quantum system. And what's an open quantum system? It's a system that has a quantum closed part that interacts with a medium. And the medium is whatever surrounds that quantum part, okay? So this, probably you know that the atomic nucleus has levels and so on, right? And you have transition between levels, pretty much like an atomic system. But it also has an unbound part that is, we call the continuum, that it's coupled to this closed system itself, okay? And the way to reveal the phenomena, that very exotic phenomena that appear because of that coupling between the continuum and the closed part, it's doing nuclear reactions. Okay, so I'm not going through the details of nuclear reactions, but it's important to understand that we do nuclear reactions and we need to detect particles in certain conditions to understand how quantum effects appear in the nucleus itself, okay? So this is the structure. I would say there's some examples of very exotic nuclei that are very rich in neutrons and stable matter. So the idea is that whether we have a highly excited nucleus or a very rare isotope with a lot of imbalance in neutrons and protons, we have emergent phenomena that come from the instability of the nucleus to retain all that, okay? So there's complex experiments to understand what are the limits of the nuclear landscape, because you have, you know, the periodic table. This is not the good one. Sorry about that. Okay. Well, okay. So we have the stable isotopes, and you can somehow unfold a much larger periodic table by considering isotope, which is the same number of protons and different number of neutrons, right? So there's features like what are the limits of nuclear existence and what features arise beyond those limits and so on. And I will explain that, how that connects with some very specific problems, general problems in particle and physics. So we know about 2,000 isotopes, and there's a lot of effort right now to create more. And this is what the goal of, let's say, modern nuclear physics is about, to understand exotic nuclei out of a balance by doing nuclear reactions. In particular, I like direct reactions because this is a way to prove several phenomena like collectivity. Nucleus are not spherical, right? They have pure shape, or they are like rugby, or if you like American football, or whatever you want to call it, shape and so on, prolate, oblate. And we prove that through very specific direct reactions. The direct reactions is that we have a projectile and we have a target and a heavy nucleus, and we do something with the projectile that is peripheral and does not disturb the nucleus. So it is like a spectator. So normally what we do is to measure the light residue. You have like a proton beam, neutron beam, triton beam that interacts with a heavy nucleus. Okay, so this is what we do. And it's not because it's fun, it's because that's the only way to understand things. Otherwise, it's very boring. So what's the very first experiment on nuclear physics? And actually, the very first experiment was the experiment by Geiger and Marsden, I would say, because they were the students of Rutherford. They prepared everything, and then Rutherford, of course, took the credit, but that's another story. I mean, I'm kidding, because obviously everything was even somehow, right? But they did just a very simple gaseous detector to count alpha particles and understand how alpha particles interact with a target. You know that because it's one of the models of the nucleus that we have that determines that, well, you have a core and something surrounding it, okay? And from that point, we have not evolved very much in terms of detection. You will see, because eventually we still use the same concept of detection in modern detectors used for not only detecting reaction, the products of the reaction, but also to produce exotic nuclei, as you will see. And this comparison, I think it's fair, because we somehow inherit all the technology from high energy physics, just mostly because there's more money there and developments go faster and they are not solid. But in a collision, for example, high energy physics collision, that you need a different proof in terms of energy to look at what's inside the nucleus itself, or even at subatomic scale, you need very high energy, and then you have a collision where you have thousands and thousands of particles that you have to track to reconstruct the reaction itself. But these particles are very small, and they have what we call, they are minimum ionizing particles. So the detection challenge is different from what we do in low energy nuclear physics, because there's one thing I haven't mentioned. We don't have radioactive nuclei in nature, at least not the most exotic one, because their lifetime is almost zero to a natural scale. So we need to produce them in flight. And that means that we have to reverse the way we do things. In this case, we need to inject a heavy nucleus inside a detector and have the target there, which means that we'll have a much heavier thing going into a medium, and will produce many different effects that are not appearing here. So the challenges are different. I won't go into the details here, but you will see that we reverse this to do the trick of increasing the efficiency of detection depending on the experiment that you want to do. So since I don't know how much about gaseous detector, I think that some people here can leave now if they want. But in reality, when you want to detect something, you need a signal, right? So the signal has to come from ionizing a medium and extracting the information that happens inside the medium. In this case, what we do is we have a charged particle, could be also neutral particles, but I focused on charged particles right now, that will go through a gas medium and will ionize it and will create positive ions and electrons that under an electric field will drift to the cathode and to the anode. So we just need a signal readout there, electronic signal readout there. There's different modes of operation. If we increase the field enough, we can multiply by collision the number of electrons, so we enhance the signal that we get from it. Okay, so this is the basic principle of what I'm going to explain right now, micropattern gas detectors. And a micropattern gas detectors is our, let's say, tool of the trade, okay? So we have an ionizing charged particle that ionizes the gas and all the electrons drift to, for example, this is a Micromegas, we have a mesh, and between the mesh and a segmented backplane, we have a much stronger electric field where we amplify the signal, okay? So this is a typical Micromegas. This is 1 meter diameter, and there's 10,000 pads of this here. So with this configuration, we are sensitive to the position of the particle inside the detector itself if we have enough money, because 10,000 channels is quite a lot, okay? And this is the typical structure here. This is the pad structure for this very specific detector, and this nice thing here is the routing of the PCB to route all these 10,000 channels into your electronic system. Simple, but effective. On top of that, we have another type of gaseous amplifier, which is the GEM. Instead of having a mesh and a pad plane, in this case, what we have is a stack of PCBs with different cathodes, anodes, if you will. So we focus somehow with the electric field, the electrons to go inside this hole here, and they are amplified because we apply a much higher electric field here. But you have to notice here that in the end, this is open. So you need to put another detection system on below that to record what happens here. So you have thousands of small holes in a PCB that act as a proportional counter, each one of them. So the principle is the same, we amplify that. And the best thing about this, there's two nice things here, is that we can combine both, because this is open, so I can put this guy on top of a Micromegas, or the other way around if you engineer a way to do it. But the most important thing for us, for doing nuclear reactions, which I won't go into the detail anyway, but it's important to know that this type of configuration allows us to work with pure elemental gases. And this is important because when you do a nuclear reaction, you want pure targets. And I will explain why that's complicated in inverse kinematics. Anyway, this works fantastic, and we like it very much, and I'm going to show many experiments that use this configuration, okay? Now, as I said before, you have to produce the rare isotopes to study them. So conventional stable experiments are like your beam. Well, you have a source, and then you accelerate them, and then you have a stable target where you make the reaction, and then you have, well, a plethora of detectors surrounding the target, and you measure angles, energies, and many things. So the configuration is usually you have a light particle impinging on a stable or long-lived isotope. Long-lived could be beryllium-10. It's a radioactive isotope, but the lifetime is something like millions of years. So one can consider that stable, others not. If you talk to safety, there's always radioactive material in a beryllium-10 sample and this type of things, but it is what it is. But as the lifetime shortens, you need another technique. So what we do is, okay, we are going to break something to produce the isotope of interest. So we have a source, we accelerate it, and then we have a production target. So we smash that, right? So like something heavy, but it has to be close enough to the mass of the isotope that you want to detect. Otherwise, it will be very difficult to produce it. So once you produce it, you have exactly the same setup as you have here. You have a target because you have to make the reaction, but in this case, your target is a light target. And then you have a heavy particle going inside your system, which makes things more complicated, but more interesting at the same time. So of course, modern facilities are devoted to provide the highest intensities of the most exotic beams for scientists that want to explore emergent phenomena in exotic nuclei. But of course, as you can imagine, this has many complications, especially because everything is boosted in forward direction, right? You have a very heavy thing. So your motion in kinematics, everything goes in forward direction. So we need to adapt our detection systems to this, okay? There's quite a lot of facilities around the world right now that are being constructed. Some others are constructed already. There is, of course, one of the most famous is RIKEN. It's a very powerful facility in Japan. But right now we'll have also the facility for rare isotope beams, which has a power of 400 kilowatt in target. That's quite brutal because that means that you have to smash something into a target that has to withstand 400 kilowatt of power, meaning that making the production target for that, it's a nightmare in reality. But all these facilities around the world can produce exotic nuclei. Of course, there's zero in Spain, but that's another story, okay? So depending on what you want to create, there's rates, right? So the most exotic species are created with rates that could be of the order of 1,000 particles per second. In direct kinematics, you normally need 1 million particles per second, something like that. Out of 1 million particles, there will be one that will make a reaction. So if you want some statistics, you better have good intensity, but this doesn't happen. So we need to compensate for that somehow. So the first gaseous detectors done for tracking are very specific. Normally we use what we call spectrometers to somehow, as I said before, identify what we produce. So we produce normally a lot of nuclei. So we need to identify them by atomic number and rigidity. Rigidity is literally the connection or the relationship between the particle velocity and the mass. So you do that with a set of detectors where you have an ionization chamber that measures, that gives you the energy loss of the particle crossing the detector itself, and that's proportional to the atomic number. Okay, we have one, but there's many atomic numbers. How we do unfold the other part? By time of flight, literally. They are fast, but our detectors are faster. Means that we can measure how much time it takes from the target to the detection system. And as you can see here, we have lines corresponding to the same mass atomic number ratio. And if you have this ratio, and if you have the energy loss, then you can identify one by one. And this is what we call a magnetic spectrometer. And in this case, we use very simple tracking detectors, not even micropattern gas detectors, but just a simple wire, segmented wire. No, the wire is not segmented, but the readout is. So you have the field, the field that drifts the electrons of a particle that's going through, and then will be amplified in the wire. So essentially, this is a very simple technique, but it can be also adapted to something that to what I showed before in terms of micropattern gas detector. But I wanted to show you this because in your focal plane of your spectrometer, you need the trajectory of each one of the particles that's going there to correct for what we call the acceptance of the spectrometer and get better resolution in terms of the reaction channel that we are measuring itself. So this is the first use and the most common one, and we need it for radioactive isotopes. I wanted to put this because I think this also highlights that it's not only for producing radioactive isotopes, but you can also do quantum physics with these tracking detectors. If you are able to produce an entangled pair of protons, which you can through a very specific nuclear reaction, which is charge exchange. So you have a deuteron that impinges in a hydrogen target, and then you have the neutron is converted into proton, and then those two protons are entangled. So for those of you that like quantum physics and like the entanglement world and so on, you can determine somehow the spin-spin correlations of these two protons to determine that in reality they were entangled beyond the Bell's limit here. So this is a very particular experiment that we are trying to do in a more complex system that highlights that with simple detectors, gas detectors, you can get a lot of information that is not only relevant for a structure, but also for things like quantum physics. We can go beyond this by measuring these things from a radioactive nuclei that deintegrates and have many particles, and we can measure the same, okay? I don't go to the details here, but I just wanted to show that it's not only about the structure itself, but there's fancy things that Now, the thing is that, how's the time? Okay. When we reverse this, we need better detectors. So our conventional setup is like this. So we have thin targets, but thin targets means that we also have less targets available. So we need to enlarge that somehow. And we enlarge it by making a gaseous detector very large, 1 meter long, where the gas itself, it's the medium for the reaction. Like hydrogen gas will be proton, deuterium gas will be deuteron, helium gas will be alpha particle. So depending on the reaction you want to do. So essentially the scheme of this is, okay, I need more luminosity. So I'm going to enlarge this. I'm going to put the beam inside. I'll make the reaction and will be electrons from the ionization of the gas itself. And I put an electric field and they will drift to a segmented micropattern gas detector, like the one that I showed before, Micromegas, stringent, where we can detect the arrival of these electrons. And we have this in 2D, and we can also determine the time of arrival of the electrons. So in reality, what we have, it's literally a microscope for nuclear reactions. You can reconstruct in 3D, and you will see the reaction itself. So it's very powerful because since it's so large, you enhance your luminosity by 2 orders of magnitude. So experiments that could not be done before with very exotic species can be done with this, okay? And the best thing, you can use a magnetic field, a very strong one, and then you have a spectrometer. Literally what you enable is through the rigidity or the curvature of the particles, you can determine with much better resolution the kinematics, and I'll show you this. Of course, we are talking about magnetic fields of the order of 2, 3, 4 Tesla. So where we get that? Normally we get them in, I'll show you MRI magnets. So these are what we call active target time projection chambers. This is the mode of operation. There's many types. There's cylindrical, there's a list of different reactions for nuclear structure, pairing, astrophysics, so depending on what you want to do. So we have different topologies, if you want to call it like that, where you have like a cylinder, where we make the reaction, as I saw before. And you have also some other configurations where you have ancillary detectors to detect particles that are punching through the gas, because those that are punching through the gas, unless you have a magnetic field, won't be useful for anything. So you can put silicon detectors, semiconductor detectors, or crystal scintillators. But I'm going to talk about the one that has nothing because it's the one I'm working in. But in reality, this is what we do, and this is what we need. We inject an exotic beam like helium-6, and in the cylindrical configuration, what you can measure every time a step, because you have electronics capable of doing that, it's where the reaction happens. And because there is gas, and this is a low energy beam, you are stopping the gas inside. So in reality, what you are doing, it's proving with one single energy, the whole excitation function of the reaction. Means that all the energies in center of mass of the reaction that are relevant to extract information from the reaction itself. And this can be done in one shot. It's very efficient. Meaning that you can do an experiment that would take literally like 2 weeks in literally 2-3 days, just because you don't have to tell the operator, please change the beam energy, readapt everything, calculate the settings of the beam again, and so on. So this is very efficient. And people that it's on the committee of for approving this experiment like it very much because you are saving time. One hour of beam time for radioactive isotopes, it's about 10,000 euros. So just to let you know what's the order of magnitude of the price of these things, okay? And this is the active target time projection chamber of the facility for rare isotope beams, where I was working. And it lives inside this magnet from Oxford, which is a 4 Tesla solenoid. It's 1 meter long time projection chamber with 25 centimeter radius. And it's equipped with these 2 micropattern gas detectors that I explained before. The kinematics, the reconstruction of the kinematics is not really trivial, because you see everything inside of these detectors, everything that happens. It can be a reaction in the gas, but it can be also a reaction in the window, because there's windows, or it can be a reaction with a contaminant. So the skill needed to understand this, it's rather complex, because you don't have information of the energy and angle of the particle. You have a cloud of points, and that's all. You are on your own to reconstruct kinematics from a cloud of points. So you need techniques from machine learning, pattern recognition algorithms and so on, and it's fun. And one of the most complicated parts is that in high energy physics, you normally have high energy particles that describe trajectories that are circular, right? But everybody here, I guess, that knows how to fit a circle if you have points, but this doesn't have an analytical solution. So you have to go step by step, calculating the trajectory if you have your model of propagation. So for this, for example, we use something that is very useful in engineering, which is called Kalman filter, which is an algorithm to guide projectiles and robots and this type of thing. So there's kind of like a multidisciplinary approach here. And you see everything. And these are what we call the cinnamon roll here, the kraken or the octopus, if you will. This is a nucleus breaking up, and everything is curved by the field itself. Okay. Now, let's talk about physics. Now we have a good background on how to use these detectors for some very exciting physics. And the question now is, maybe I can ask you how much you know about the neutron, but in reality, there's one thing that we don't know very well about the neutron. We know that it decays, but if it lives inside the nucleus, it's stable, and it forms pairs with neutrons and protons, okay? So we know this very well. We still do not know why deuterons exist out of the nucleus, but when you put a deuteron inside of the nucleus, it's not bound anymore. This is something that many people would say I'm saying it wrong, but this is more or less the idea. But in reality, there is something that we don't know yet. It's what is the lifetime of the neutron itself, because two different experiments are giving different results in terms of the lifetime. And actually, 4 sigma of difference. So this is the lifetime of the neutron. So you have quite a lot of difference. I mean, it's very large, 1% difference. So for the degree of precision that we have nowadays, it's inconceivable that we have a 1% difference between 2 different experiments. But the experiments are literally, you can put neutrons in a bottle because they can scatter inside the bottle. So you can put them inside and you can count how many disappear, and that would be a way to measure the lifetime, right? The other way we have is that this is called the bottle technique, and this is the beam technique. In the beam technique, you measure how many are converted into proton and so on. So these 2 techniques that are the only ones, as far as I know, that we have, or at least the most precise one, give 1% of difference. So actually, this is a proof that you can put neutrons inside a bottle and pour them inside a detector. These are ultra-cold neutrons. So they are so low energy that they bounce inside the bottle without dying, and then you can move them from one part to the other of your laboratory. Of course, it requires a lot of money to produce ultra-cold neutrons because you have to moderate them a lot. These are energies that are nano-electron volts, for those of you that know how to convert that into energy. Some people just speculated that this may happen because the neutron might be converted into a dark sector. Dark sector is a type of particle that would be related to dark energy or dark matter itself. Of course, right now, this is completely ruled out, but this serves as a playground for us to do experiments. And this hypothesis was highlighted in what we call halo nuclei. Like, for example, beryllium-11. A halo nuclei is a nucleus that has a core and then has a neutron that is farther away from the core because of its wave function itself. So the question is that if you can detect the product of the decay of beryllium-11 in this case, you will have an idea of possible decay rate into a dark particle from this particular nucleus. So in the end, what you will have is a beryllium-10, because you lose 1 neutron, and that neutron goes into a dark particle, okay? And there are several hypotheses for this. There are different types of particles that this can disintegrate, but in the end, this is the only one that has not been ruled out somehow, okay? But there is something that these people didn't know, is that in reality, there's a decay mode in beryllium-11 that leads to exactly the beryllium-10 residue plus a proton. It's when beryllium-11 decays by beta emission. So someone did an experiment where they implanted into a foil beryllium-11, many beryllium-11, and then they brought that to an accelerator and figure out how many beryllium-10 they had left in the foil itself. That could be a proof of something was transforming beryllium-11 into beryllium-10, okay? Indirect proof. And the ratio branching ratio was the order of 10 to the -6. It's quite high for such exotic decay because there's something that you have to take into account here. Beryllium-11 is a neutron-rich nucleus. Okay, so it has 4 protons and the rest are neutrons, which means that in reality, as anything in nature, it will expel what it has, like neutrons. There has an amount of neutrons that it's not stable. But instead, what we are observing is that it's emitting a proton. So how that can be possible? Because that somehow rules the energetic of that decay. In reality, it's more complicated than this, but we did the experiment to measure the decay of beryllium-11. We implanted it to a TPC, time projection chamber, and we let it decay. Normally it decays by emitting a lithium-7 and an alpha, but sometimes, which we determined to be 10 to the -6, sometimes it emits a beryllium-10 and a proton. So that way, we have a direct way to somehow figure out how many times we have a beryllium-10 plus a proton and how many times someone would have a beryllium-10 plus a dark sector. And it turns out that there's no room for dark particles here. But the thing is that this experiment is very complicated because the energy of the proton is very, very small. So the only way you have to do this is to use a gaseous detector where you can detect somehow the shape of the energy loss along the track of the particle itself. And this is for a proton, and this is for a lithium-7. So we implanted millions and millions and millions of beryllium-11, and in the end, we got something like 300 protons with this technique, and we figure out the ratio. This happens in 2019, and there's still quite a lot of controversy regarding the existence of this very particular decay, but we are running out of time, so I have to move forward. But of course, we ruled out somehow that the dark decay was a possibility in this kind of system. So this is something very nice. So there's another very exotic decay. So you know that there are several very well-defined forces in nature. Okay. So through an experiment of resonance scattering of a proton into a lithium-7, that forms a beryllium-8 nucleus. And this group in Hungary determined there are several decay modes, right? And one transitions, it doesn't matter, but what matters is that these transitions emit a positron and electron, particle and antiparticle. So by measuring the angle, they can determine that there's an anomaly in the angle of the emission of this positron and electron. Okay, this is all you need to know. And what this means? It means that by kinematics, in normal conditions that we know by electrodynamics, this decays by emitting a photon, and that photon is very forward boosted because there's nothing faster than photons. So the electron and positron are emitted in a very forward direction. So there's no rule for wider angles unless you change the particle that the beryllium-11 is emitting. And then if you emit something that's slower, the internal energy of the electron and positron will make angles much wider, right? And that's what they observe in several transitions. And they claim that this is a new force, new boson, which is quite a lot of claim, actually, in nature, right? Of course, no one believes this because they repeated the experiment again and again and again, doing the same thing. And there's experiments trying to do the same with TPCs, because this was done with a plastic scintillator, which is a passive detector, let's call it like that. But there's people trying to use spectrometers with time projection chambers and magnetic field to detect this positron and electron that will go in opposite directions because of the charge inside the TPC. This is an experiment that it's not done yet, but it's being designed in the Czech Republic, but we did something similar. So we make the reaction on a lithium target here. We produce beryllium-8, and it decayed. And we were able to observe these pairs. Okay, so we observe with a magnetic field inside our TPC, the bending, what we call seagulls, the positron and the electron there. This is not analyzed because it's impossible to analyze. What I'm showing here are the best events, but electrons scattered a lot in the gas, and it's very difficult. Okay, let's move to another interesting topic where micropattern gas detectors and solenoid magnets are also important. So, you know when you have antimatter usually annihilates with matter of the same type, right? So you have an antiproton, it annihilates with a proton itself. So if you have read that book by Dan Brown of Angels or Demons, it's called, where they put actually antimatter inside a bottle. This is what we are going to do here. And actually we are going to transport it. So you'll see. Antimatter is another proof of measuring the shape of the nucleus. In particular, the skin of neutrons. When you have way too many neutrons, they rearrange in a skin around the core, or the halo tail that I explained about. So when you have an antiproton decaying, the antiproton goes into the nucleus, and the first thing that antiproton will do is expelling the electrons on the surface, okay? So there will be electrons everywhere. Then they will collide and annihilate with the surface of the nucleus itself. So they can annihilate with a proton, but they can also annihilate with a neutron, which is not the antiparticle. It's just because of the internal structure of the proton. We want to do this experiment. So we want to use antiprotons as a sensitive proof for the shape of the nucleus, and in particular, the distribution of matter inside the nucleus itself, as you can see. Now, the question is that you have to create those. And how you do this? So essentially, you produce antiprotons, and you can trap them, okay? So there's something called multi-reflection trap, where I can put a proton. It's a electrostatic magnetic trap, where I can put protons inside and make them oscillate all the time. What's the lifetime of a proton? The same as an antiproton, the same as a proton. Should be living forever, unless it annihilates, okay? So you can trap them if there's nothing there inside. So we have this, okay? And once we have everything trapped here, we have the magnet, and we have to make the collision with the nucleus that we want to explore. So you need to inject in another trap the nucleus itself. So you have one trap with antiprotons and one trap with the nucleus itself, and then you open the door. It's not a door, of course, but it's kind of like a gate valve, and they meet, and then annihilate, and they are measured in a time projection chamber, like the one that we explained before, and emit pions, light particles itself. But this is not the end of the story, because you want to do this, as I told you before, all these phenomena of halo and nuclear skin and so on does not appear in stable matter, meaning that you have to bring this somewhere else to do the experiment, and means that you have to produce exotic nuclei and inject them, okay? So this is the trick here. This is the CERN. This is the CERN map somehow, and this is ELENA, which is the factory for antiprotons. So we have our system that weighs 10 tons here with the solenoid, the time projection chamber with our micropattern gas detector. So we put it inside. We put the antiprotons inside the trap, and we need to bring them where the exotic nuclei are produced. Unfortunately, there's no connection between two buildings. So we have to bring this with a truck all around CERN and bring it back to Isolde, which is the facility to produce the exotic beings. So, you know, that book was not exaggerating at some point, because we are transporting antimatter. And I think that I'm going to talk about directional detection just 2 minutes if I have the time, because I'm arriving to the neutron part actually somehow. So the last thing that I want to comment on the use of micropattern gas detectors is for directional detection, okay? Directional detection is a way to detect rare events by averaging somehow all the events that you have. So you have a fiducial volume, large volume, that you want to detect something like neutrinos, dark matter, and so on. These are very rare, and they do not occur very often. But there's a lot of contamination everywhere. Here we have a lot of neutrons coming from cosmic rays, right? And these big detectors will see cosmic rays. So there's nothing that says that background won't be isotropic, okay? So somehow you need to measure inside your time projection chamber the direction of the recoil of the particles coming from the interaction of the background inside the time projection chamber. So you have a big volume and you have neutrons going everywhere, and on average you will have a direction that is isotropic. That you need to map out somehow to figure out what would be a signal on your detector that would say, okay, I have a rare event here and so on, okay? So it has applications in many things. Exotic ones like dark matter, I wouldn't call it exotic, but complicated ones like dark matter and neutrino physics, but also for neutrons. Neutrons are also neutral particles, and through the recoil inside the detector, because it's a gas and we can measure the recoil, you can reconstruct kinematics or do imaging of the detectors. Okay, so how this is employed somehow? There's one example here. Directional dark matter. As I said before, we have a detector that is sensitive to the direction, so we are going to use it to detect hypothetical directional dark matter. What is this? Well, another hypothesis, as you see, for dark matter. There's many of them, but this is fun at least. So we are in the solar system, so there is what we call a WIMP. It's a massive particle coming from dark matter, wind, that may come from the center of the solar system by gravitational arguments that I have no idea about, but this is what I've been told. So essentially, since we are in the solar system and we are rotating here, with respect to the center, we should see some difference, right? Depending on where we rotate. So this is what essentially what it's depicted here, right? You have the wind, and then you have our Earth that, depending on the season, will rotate with respect to the wind in one direction. So if we have a detector that is sensitive to that direction, as I said before, then we can look at the recoil. So that would be the gas in the detector, and then we have the wind interacting, there will be a recoil. Very low energy recoil, and this is what you see here. This is it's not that we have measured dark matter, but through different interactions, we can calibrate the detector. And in this case, well, here you have, for example, an example. You have the dark matter, and there will be a helium particle, for example, that recoils. And if it recoils on an electron, for example, a gamma, because the electron is much lighter, it will suffer a more tortuous path. It will scatter everywhere. So you have a topology that you can distinguish between these two events. But here we use another technology. Instead of measuring the charge in the time projection chamber, we measure the light that is emitted in the gas, because you can have a much better resolution with a CCD camera, the same camera that you have in your phone. Not exactly, but you could use it to image what happens inside the detector, and these are typical tracks. And the last thing that is related to this is that you can also do directional dark matter through what is called the Migdal effect. Migdal effect is something that has not been observed yet, and there's many people trying to observe it, which is what happens kind of like a dipole, right? You have a neutral particle colliding with the nucleus itself, and then it has a recoil, but the electrons do not have a recoil because you have not touched the recoil. Of course, this has an electric field that will influence the electrons. So because of this recoil, there will be a Migdal electron that will be emitted from the cloud of electrons, just because of that. So essentially, the idea is to use this because it would be very sensitive to the energy of the dark matter particles that we want to observe. And this is something that simulates what would be the dark matter, a certain dark matter particle with a certain mass, with a certain energy that will recoil in a nucleus, and this will be the electron that's emitted there. So there's a big collaboration trying to do this, and it's exactly the same type of optical TPC that I was talking about. So using a camera to image high resolution tracks there, okay? I think that this might deserve a Nobel Prize if someone can measure the Migdal. I mean, not the people who measure it, but probably who hypothesized the Migdal effect, because it's normally what happens. And I think this is all. I didn't have much more, so I hope that, well, at least you somehow enjoyed the talk, and of course, I'm open to any question that you may have. Thank you very much for your attention.
Thank you very much, Yassid. Incredible advances from the time I cared more about detectors than I do now.
I hope we can leverage them, yes.
The last 15 years have really shown that you can do much, much more. Any questions from the audience? Paula.
Do you mind telling us what your company insights is?
Yes, of course. We are going to use all these detectors, okay? For example, the last part that I did not explain, all these detectors are perfect for neutrons, as I said before. Most of the background that we have at this level are neutrons. So these type of experiments, they suffer a lot from neutron background, which make these cryogenic detectors, in this case, it's like a gas detector, but it's cryogenic, so it's liquid. But the principle is more or less the same. So since these detectors are very good for neutrons detection, we are engineering them in a way that we can use them as a very efficient imager detector. And that what means? That means that, for example, liquid argon, you don't have to go to the expensive part. Liquid xenon is much more expensive. But if you can have liquid argon, the efficiency of the detector of detection of fast neutrons of about 1 MeV, 10 MeV energy in a slab of 3 centimeters of liquid argon, it's of the order of 95%, which is a lot compared to other detectors. But that's not the only the interesting thing, is that through this scheme here, where you can measure scintillation and also, well, you can measure scintillation here and electrons or scintillation here, you can reconstruct the position with sub-millimeter resolution here. So in the company, what we are trying to do, and hopefully together with Félix at some point, is to be able to engineer this to be used with low-intensity neutron sources, like could be like the compact accelerator neutron source, CANT, so we can deploy that in field somehow. So it's a way to compensate for the low intensity of the portable sources using a specialized detector technology, let's say like that. We do many other things, but this is probably the one that's more connected.
Probably things you cannot tell us.
I could, but I will have to kill you.
Just following up from that question. So I presume that, for example, the directional detection has been used for, I could easily see how you can use that to do tomography without having to rotate the sample, right?
Yeah.
So you get everything in one shot.
Yeah.
And you don't have to spend, has this been demonstrated?
I don't think so. I don't think so. But it will be a nice procedure to do that. Also, you can have quite a modular system, depending on where you want to do your radiography, right? I mean, if it's something that you cannot access from behind, you can also use kind of like this modularity to do the tomography as well from the backscatter of the neutrons and so on. So there's quite a lot of things that can be done there.
And perhaps as well, scattering as well.
Yeah.
You could be actually imaging, being able to do position-dependent scattering from the use of these technologies, right?
Absolutely.
And you are not aware of anybody who has?
No.
Me neither.
No, this is important. There's many things also with this. For example, one thing I haven't said is that the time resolution of these detectors is good enough to do transmission imaging, energy resolved transmission imaging. So with this, you would be able, of course, you need a pulse source and so on, but imagine that you have a pulse source, you have 1 nanosecond of resolution with these detectors. So this, yeah, it should be more than enough. What you can do with this, the interaction of the neutron inside the material that you are trying to sample is subject to nuclear interactions. And those nuclear interactions are somehow revealed as a pattern in the velocity of the neutron on the time of flight, which is the neutron resonances there. So if you can detect or you can measure the velocity or energy of the neutron in each one of the pixels that you are imaging, you have a way to distinguish what type of material is inside the sample that you are imaging, because those resonances are a fingerprint of each one of the nucleus that we know. All of them are different because of the structure of the nucleus itself. And that's probably one of the most interesting things that one we can do, because you can really have a tomography and say, okay, I have plutonium here, and then I have an explosive here. So this person is trying to make a dirty bomb or something like that. Well, I don't want to put that in the worst scenario, but yeah, you can.
You will get money for that.
Absolutely. Not in Spain, but countries like, for example, US and UK are very concerned about border security, and they put quite a lot of money on this. That I cannot say.
Any other questions? Please.
Regarding the dark matter search that you show there, you said that you would be able to reconstruct the nuclear recall from a WIMP.
Yes.
Okay, that's the plot that you show right over there, right?
Yes, this is
I have a question related to the detector that you used in order to be sensitive to that wave. What's the dimension and the pressure or the density of the gas that you are using? Because when you think of dark matter experiments, they are very large and they use big.
Yes. From what I know, I don't work on this. This has to be gas, so the density it's quite low in that regard. So I cannot give you a number in terms of the cross section or the number of events that you may get. But the only thing I can tell you is that this is pure CF4 at 150 torr. Otherwise, you wouldn't see a recoil at all. Now, maybe someone more expert here on WIMPs can tell me if that's enough density to detect something, but yeah.
Okay, I was just wondering if you knew the parameters in order to see WIMPs.
I don't know. I'm interested in the technology. As always, there's always something that you can get out of these very expensive developments for other type of fields. So in my case, for example, as we were discussing here, this could be a very good way to detect neutrons as well. WIMPs, we don't even know if they exist. So.
Okay, thank you.
Any other questions? I have one last. You mentioned before resonances.
Mm-hmm.
What about coincidence detection, neutron gamma? Is that something
that has been done already? Actually,
to reduce backgrounds as well?
Yeah,
actually,
yeah. But you are talking about, for example, generating neutrons through a nuclear reaction and detect. Yeah. So, for example, when you generate a DD, you put a DD, you have the neutron, and then you have the helium-3. So the most efficient way to do this, if you have a pulse source, you can do the coincidence with the detection of the gamma with a detector that has enough resolution. But another way to do it is by tagging. You can tag the helium-3 that it's produced in the reaction, and then that will give you the start point, and then you have the neutron, it scatters out of something, it excites that to a point that emits the gamma, you detect the gamma. So the difference between that time of the helium-3 and the gamma tells you the time of flight and then the depth of what you are imaging. And that's something that there's proof of principles of this from a French research group that did all that already.
Just simply unthinkable 10 years ago.
Absolutely, absolutely. But they stopped because no one was providing the